So, welcome everyone. Thank you so much for joining us. My name is Emma Bernard, and I am a program coordinator at the Mid-Atlantic Regional Association Coastal Ocean Observing System, and I'm one of the many people who was organizing this workshop. So, thank you so much for being here. Before we get started, I wanted to very quickly run through our agenda. We're going to have an introduction from Gerhard Kuska, my boss, and then move on to John Wilkin will be giving us an introduction to ECCOFS, and Roy Young-hee will be giving us a demonstration of it. We'll have plenty of time for Q&A and then move on to breakout discussions before a further Q&A and opportunity to provide feedback. So without further ado, Gerhard Kuska is my boss and the executive director of Maricus. He also is the chair of the IUS, Integrated Ocean Observing System Association, and he is going to tell us a little bit about the background for this project and the different organizations that are part of it. So take it away, Gerhard. Thank you.
Thank you, Emma. If you could hit the next slide. So good afternoon, everyone, and welcome. I'm really pleased to see so many folks here. I know we'll be getting more folks coming online in the next few minutes, but we're going to get going because we have a lot to cover today. My task today is to just give a bit of background that many of you, especially those involved with IUS and with Maricus in particular, will be familiar with. We are a public-private partnership, part of the U.S. Integrated Ocean Observing System, a federally established public-private partnership of 17 federal agencies and 11 regional associations, all certified by the government to collect a variety of both physical, biological, chemical, and even in some cases meteorological data that then have an application in society towards societal benefits. The things we focus on are important to funders. They're important to our communities and citizens, and include things as basic as safety, security, jobs, and the economy. Now, we do this by focusing on thematic areas that our stakeholders and user communities care about. Things like maritime transportation and commerce, coastal hazards, which include things like flooding, hurricanes, fisheries and natural resources, important across the entire country as a food source, but also as part of our ecosystems as a whole. Water quality, which encompasses a variety of sub-thematic areas, and of course, energy, an important and growing area for our offshore waters. Now, you can see in the Mid-Atlantic, we have an interesting footprint. We have 5 watersheds. We have 10 states in the District of Columbia, about a quarter of U.S. population, and we were established back in 2004. Interestingly, like many of the regional associations, we grew out of traditional academic partnerships and collaborations that had been established long before IUS was created. So most of our partners, both academic institutions, but also government, nonprofit, and private sector partners, had been doing business in one way or another, or working and collaborating for a long time. And they form the foundation and the important expertise and an engine of what drives a lot of what IUS does and achieves. Now, if you can go to the next slide, Emma. I mentioned 11 regional associations. As we talk about not just data collection, but today we're here to talk about ECCOFS and modeling and that which will be derived from that. We have a series of pillars within IUS. I mentioned data collection, engagement, getting to the customers and users, understanding their needs is a critical piece of what we do, not just for our partnerships, but also for the partners and federal government to help them evolve and better focus their resources and their products for the communities. Now, this effort that John and Roy Ying are going to talk about today, the ECCOFS, includes 5 regional associations. I think if you hit a button, it's going to highlight all of them. NERACOOS are partners in the Northeast Regional Association Coastal Ocean Observing System. SOCORA, directly to the south from North Carolina down to Florida, Southeast Coastal Ocean Observing Regional Association. Our partners in the Caribbean, CARICOOS, and our partners in the Gulf of America, GCOOS. So a large footprint, a large area to cover. I think one of the hallmarks of ICE is that not only do we work well together with our federal partners, we also work well across the regional associations. Not only do we all work towards the same standards, the same level of quality assurance and quality control of the data, but we also work together on common products, sharing information, and sharing expertise. So we have partnerships already in place in many areas. So it is not the first time and it is not new for us to be working together across regional boundaries. I think in the case of what we're talking about today, John Roy Ying, Andy Moore, and some of their colleagues are the perfect leaders to lead this effort on ECOFS. And it's a very exciting time to be evolving and advancing this work as funding becomes more focused, other challenges that we're facing are things that we're doing together, and the value of what's being done here is going to become more important and be something that we need to highlight more towards the communities, towards the funding down the road. Last slide. I also want to highlight one of our core partners for some time, Tetra Tech. Many of you know them, the companies that Tetra Tech has recently purchased, including RPS and Axiom. But the Tetra Tech Ocean Science team has been working with us for a very long time through those other partners. In our case, in the Mid-Atlantic, RPS has been our partner for most of the time, I would say since the beginning. They also run Maracus Oceans Map, a sub of the larger Oceans Map data ecosystem platform. Sometimes people refer to it as a portal, but it has a greater capability. And each of the regions has different capabilities, different ways of delivering data, of storing data, of distributing and creating products. RPS has been a strong partner for us from the beginning and does much more than just the things that they do for us, including working with the energy sector, including working with modeling, including working with a host of other cyber infrastructure areas. With that, I think that's my last slide. I'd like to turn it over to John and then Roy Ying to go into the background of ECCOFS and to move into the demo. John?
Actually,
Okay.
first, we're going to do a really quick poll before I'll introduce John. Throughout this workshop, we're going to be doing a few different polls to collect information on and your feedback just in the moment. It'll be really quick multiple choice, but first we're going to ask that people fill out this really quick poll telling us where you're from, what your relationship to the ocean is, and maybe what your favorite sea creature is. And this is just, we can share the results and have this real fast before we move into John's presentation. Alrighty. Still lots of answers coming in. And then I'll end it and we can kind of see where different folks are from. The flow is slowed a little. Oh, No, it's picking back up, sorry. Alrighty. I am going to end the poll and share so we can all see what the spread is of where different people are from. And you can also click on view details to see some of the fun sea creatures. I know that's always a good one to see. Alrighty. I'll stop sharing. And I wanted to really quickly introduce John Wilkin, who's a professor of marine coastal sciences at Rutgers University and is the principal investigator on ECCOFS. John has decades of modeling experience in the US, Australia, and New Zealand, and he's a developer of the Regional Ocean Modeling System, also known as ROMS. So thank you for being here, John. Thank you for all of your work on this project, and feel free to share your screen and take it away.
Okay. Are we seeing the right version of
Yes,
my PowerPoint? We're good? Okay. Thanks for that introduction, Emma, and thank you for the background, Gerhard. As Emma said, I'm a professor at Rutgers University. I lead the Rutgers Ocean Modeling Group, OMG, and my science co-investigators in this project are Roying He, who's on the call from Fathom Science Incorporated, and Andrew Moore at UC Santa Cruz. There's a team of roughly 10 or so people that are working at different levels of part-time activity on this project, spread across Fathom Science and UC Santa Cruz and here at Rutgers. And this effort is funded by NOAA, and it's the intent is to develop a forecast system for the East Coast that it will eventually move into operations within the Weather Service within NCEP in around 3 years or so. I want to give you a little bit of background of how we got to this point. And Gerhard mentioned a couple of things here. Oceans Map, which is this view of observations and models and all kinds of things that you can see for the Maracus region of IUs. And here's one example. So we here at Rutgers, we developed an ocean forecast system based on ROMS, the Regional Ocean Modeling System, which for historical reasons we referred to as DOPIO. You might hear that mentioned in around the place. And so here's an example of hourly velocity, surface currents that you can see. This happens to be 3 p.m. Eastern Time, August 3rd. And those hourly estimates of ocean surface velocity were through the efforts of Tetra Tech that Gerhard also mentioned. Tetra Tech ingests those data into the environmental data server that is presents guidance to the Coast Guard. So these forecast velocities out to 3 days from now or 2.5 days from now are available to operators in the search and rescue operations at Coast Guard. And we're very proud of the fact that if we look at statistics of the different information products that Coast Guard goes to, they really like our ocean current forecasts for the Maracus region. And they've been one of the groups that have said, hey, can't you expand this to a larger domain so that we can have this guidance, not just in Coast Guard District 1 in the Northeast, but across the entire East Coast. So we've listened to that. We're taking that request on board. Another sort of stakeholder community here is, this is a three-dimensional analysis and forecast of the ocean. So here I'm displaying the bottom temperatures. You can look at this layer in Oceans Map yourself if you want. You can see relatively cool waters at the bottom associated with the Mid-Atlantic Bight Cold Pool, which will be an oceanographic feature familiar to those of you that work in this area. And our ability to present a good forecast of this depends a lot on the fact that we are now getting quite a lot of observations of bottom temperatures from fishing vessels in the Northeast Fleet that are participating in the EMOLT program, Environmental Monitors on Large Trawlers, which is coordinated by George Maynard. I've got his email address here in the corner at NOAA Fisheries. There are other sources of observations shown in the plot in the middle from Argo floats and gliders, but these blue dots through here are showing the extent of this network in the Northeast. It's providing us very good guidance on what bottom temperature actually is. And then every Friday when George sends out his email sort of newsletter to the fishing fleet and to others of us engaged in EMALT, he makes a little plot here shown on the right with little dots. If those dots were red, it would mean our forecast was too warm. If they were blue, it would mean our forecast was too cold. What we like to see is this Goldilocks zone of gray dots where it shows that we're doing a very good job of predicting what the bottom temperatures are. And this is actionable guidance that the fishing community are happy to have. And it's a great partnership because they telemeter observations back to us. There's an example here on the bridge of the Mary Elizabeth. There's a little box that connects via Bluetooth to sensors here that are on the fishing gear, gets that bottom temperature data, downloads it, sends it by cellular comms, and we get those data within 24 hours, and we can assimilate them into the model. So just a couple of examples of how we started developing this forecast capability. So what is ECCOFS? Following the lessons that we learned with the Doppio modeling project for Maracus, we now will have a much larger domain. I will show some all these details as we go forward. It will extend from the Orinoco River mouth to the Grand Banks of Newfoundland, which covers the 5 regional IUS associations that Gerhard highlighted in his introduction. It'll be higher resolution, 3 kilometers instead of 7, a longer forecast, 5 days or potentially longer. We're using higher quality meteorological forcing from NCEP, and we've made a lot of improvements to our data assimilation methodology and our quality control of the observations that get assimilated. And we're trying to work hand in hand with our sort of stakeholder and co-application developer community by providing tools that will make it easy to work with output from the ECCOFS modeling system. So I will jump right into the details of what we're building with ECCOFS. You can see the model domain here on the right, just showing the bathymetry. It has a vertical resolution of 50 levels. So no matter what the water depth is, there's always 50 levels. So on the continental shelf, 100 meters to 50 meters deep, there's 1 to 2 meter vertical resolution. As I said, the horizontal resolution in the forecast is 3 kilometers. For those of you that have some familiarity with the way we do data assimilation, variational data assimilation with ROMs, you might know about these inner and outer loops that we iterate on. They're done at 6 kilometer resolution. There's a great economy in the cost of doing it that way, and that kind of matches the limits of the resolution of the observations that we have. That's kind of the limit of the information content. So we're working with that in this development. I'll say more about the observations in a couple more slides, but we're assimilating temperature and sea level from satellites, in situ observations in the water of temperature and salinity. I'll say more about those. We don't yet have assimilation of HF radar currents or sea surface salinity, but that will be part of the development path in the coming years. The external forcing to this, at the open boundaries, we take the oceanic conditions in the rest of the North Atlantic from the European Copernicus Mercator Ocean analysis. We found that to be the most skillful operational global forecast system from the community of Ocean Predict developers. And to that we add harmonic tides at the boundary. The Mercator Ocean model does not have tides included. And we have the lunisolar, the sun, moon, gravitational tide generating forces. Meteorology and rivers, I'll just go to the next slide and say a bit more about those. So we are merging 2 products from the National Weather Service. The 3 kilometer resolution HRRR, high resolution rapid refresh, which gives us a 48-hour forecast in the little green box here in the map figure, which is expanded here on the bottom left. That does not cover all of the Caribbean. It doesn't cover the entire ECCOFS domain. So outside of that box, we merge that with GFS, the Global Forecast System. So this is the National Weather Service's global operational forecast model. We've got a lot of freshwater inputs into this domain. So what we do is we take daily estimates of the river discharge from GLOFAST, the Global Flood Awareness System, which is a product that comes from European Weather Center, ECMWF, where they apply a river routing model to the surface water runoff. And picking all the rivers with an average discharge of more than 50 cubic meters per second, On average, we end up with about almost 100 point sources around the coast of North America, Canada, the Gulf, and Caribbean, and the north coast of South America. So those are the external forcing inputs. In ocean modeling, if you just run the model with those external inputs, it will tend to drift away from reality. You know, we all know that our weather forecast is good for 3 or 4 or 5 days, but not necessarily for a month. And the way in weather prediction and in ocean forecasting that we keep everything as close to reality as possible is we take all the observations we have and we assimilate them in a formal mechanism to come up with our best estimate of the ocean state before we create a forecast. So here, just to give you a sense of the kind of observations that are available to us that we are already assimilating, there are observations in the water at these little red stars. The black lines are the ground tracts of satellites with an active radar that measures sea surface height, altimeters. And there's several of them on orbit: Sentinel-3A and 3B, Sentinel-6 Michael Freilich, SWAT, and a couple of other satellites, Cryosat, Altiga. So ultimately, we will also be assimilating those fishing vessel observations, the blue dots in here, salinity sensing satellites, and as I mentioned, the HF radar network that IUS maintains measuring ocean surface currents. If we look at how many observations there are per day, typically it's around about 3,000 observations per day. It's heavily weighted towards surface temperature from satellites. But there are a large number of in situ observations as well. And just to give you a bit of sense of that, in the bar graph at the bottom, you're seeing 100 or more observations down to about 2,000 meters. Those are these so-called Argo profiling floats. There's also an added sort of chunk of observations here down to around 1,000 meters. Those are mostly autonomous vehicles, gliders, operated by different IUS regional associations and research projects. And then there's a slug of observations near the surface from moorings and surface drifters. So all of those are being assimilated. Our cycle of doing this is that I'll say a little bit more about this in some coming sort of cartoon slides. We take all the observations we have in a 3-day interval, and we sort of iterate within this interval to come up with our best estimate of what the ocean looked like during those 3 days. And then we say at the end of that interval, that's our best estimate of the current state of the ocean, and we launch a 5-day forecast. Then the next day, we do this all over again. So our 3-day analysis interval kind of slides along, and there's always a 5-day forecast. We're finding that this is feasible to do in terms of the computational effort on the high-performance compute cluster that we have at Rutgers. But we're also evaluating the speed and the cost of doing this in Amazon Web Services, AWS Cloud, and the in-house high-performance computers at NCEP. Okay, so I want to give you a crash course in data assimilation. I know there are people on this call who understand this stuff, very, very well, but others of you that are not so familiar. So I'm going to have a couple of quick cartoon sketches here. So say, through time, I'm going to I want to make an estimate of the state of the ocean. What do I mean by the state? I mean the temperature, salinity, the velocity, the sea level height. Put all of those things together in a big matrix or a vector of numbers, and I'm going to call that X. That's the thing we want to know, right? That is the state of the ocean. So emphasizing that's in 3D, little 3D glasses there, so you're with me. So when I talk about X naught, the initial conditions to my forecast, it's temperature, salinity, velocity at every grid point in my model. And I run that forward with the winds from NCEP Weather Service and the rivers from GLOFAS and the tides and the open boundary and all of that. And I produce some estimate here of the state of the ocean between today and tomorrow. So there's my forecast. Okay, so time goes on. Today becomes yesterday, tomorrow becomes today. We've made some observations of the ocean state, the little red X's here. They don't exactly match the forecast. Okay, we know that in weather forecasting, it's not exactly right. It's pretty good. So then we say, well, how could we have made it better? And the way we would do that is we might change the initial condition, so the state of the ocean yesterday. And if we ran the exact same model, hey, presto, the blue line, my revised estimate of the ocean state compared to yesterday's forecast is a much better fit to those observations. So that will mean at the end of the analysis, which is now today, I will have a better state of the ocean for which to produce a forecast. And then we're just going to go through this cycle. So we need to come up with some estimate of the initial conditions here, X star, compared to my prior guess, the X naught. So it's all about how do we get X star. So we've got some good advice here, which is try using math. Okay, so, and we have a bunch of math for that. So here it is. In a nutshell, this is my ocean forecast model, ROMS, and then through the magic of variational calculus that some of you will be familiar with, some of you will remember as a real torture during college. We have a way of estimating how the misfit between the observations and our original forecast informs us about how that those initial conditions should change. So just to kind of hammer the point home, here's my original forecast. This is produced by the ROMS ocean model. And then my observations come in and they don't quite match. So if I look at those mismatches in the observations, so that's all of my satellite data, all of my profiling floats, all of my gliders, all of the radars, all of the fishing fleet data. I use those mismatches in the observations to force this adjoint model that I alluded to very briefly in my introductory remarks. And that model data error forces this adjoint model back in time to the start of my analysis interval. And then using the math, I have a way to methodically come up with a change to the initial conditions that is optimal in some sense, that will minimize the mismatch between the observations and the new analysis. So then I produce my new analysis. Look at that, it goes through all of the red diamonds, it matches my observations perfectly. And now I've got a better estimate than the previous forecast of the state of the ocean here at day 3. I produce another forecast, and then, as I said, we just chug along, we do this, we repeat this over and over every 3 days. That's kind of, in a nutshell, what we're doing. So how well are we doing? So I'm just going to show you a couple of examples from the ECCOFS model output, and then hand it over to Roy Ying to show you a little bit more about how we're visualizing these outputs at the moment. But what you see here on the left is our analysis of the sea surface height from last week, the 25th of July. And here on the right is the same analysis from the European Copernicus program, Mercator. So they are also assimilated observations, the same sorts of observations. We're taking a regional focus. We're trying to get our Western North Atlantic simulation as good as we possibly can. Mercator are doing this globally. So we're trying to improve upon this. You can't really tell from this plot. I'll look at sea surface temperature. What you start to see here, perhaps emerging, is that we have a lot more fine scale variability in our analysis than is even in the satellite observations. How can we look at this in a little bit more detail? I'm just going to zoom into a couple of places. And what I'm comparing here is the ECCOFS analysis on the left, the same information from Mercator, Copernicus on the right, and down here in the bottom are the observations from LEO, low Earth orbit satellites, which measure in the microwave, give us very high resolution temperature observations, but they cannot see through clouds. Microwave satellite estimates that are not as highly resolved, but they can see through clouds. We merge all that together and it goes into the assimilation. So compared to the Mercator analysis, which is around about 12 kilometers, and we're at 3 kilometers, you see there's a lot more detail in what we would call the sub-mesoscale turbulence. So by going to higher resolution and a few other things that we've changed, we're capturing a lot more variability and shorter timescales and space scales in the analysis. We get slightly different rendering of cold upwelling on the Yucatan Peninsula and other details. If we look up in the northeast, and here's, I think, a key point, comparing the Mercator analysis on the right to ECCOFS, we've got a lot of cold water here over Georges Bank. The Mercator model does not have tides. Tides are extremely important to mixing in shallow waters over Georges Bank and in the Gulf of Maine and here in Browns Bank. So by adding in some more dynamics and paying more attention to the configuration, we've got a much better analysis of ocean surface temperatures in our ECCOFS model. And if you sort of peer closely, I think you will see a lot more fine detail in the predicted sea surface temperature. So just sort of a rogues gallery there of things that we are modeling: the sea surface height, temperature, salinity, and the magnitude of the surface current, which clearly lights up the Gulf Stream and rings here from the separating loop current, and variability in the Caribbean. That takes one snapshot of this model state. All variables in all 3 dimensions is about 2 gigabytes. So we're generating maybe 50 gigabytes of data a day for hourly snapshots. It takes about 30 minutes to do the forecast, but maybe 8 hours to do the data assimilating analysis. We're working on ways to accelerate that. And we're working in conjunction with colleagues at Tetra Tech to make these outputs analysis ready for the cloud. We will be storing some of the outputs in AWS Cloud, or possibly moving it to the NOAA Open Data Dissemination Service, again in AWS, so that any of you on the call who want to start working with products, we should be able to make sort of example outputs available for you to experiment with. There's some browse products at ECCOFS.Fathom Science. You're going to hear more about that from Roy Ying in a moment. And what's our development path? Okay, so we've got lots of new things that we're doing with 4-dimensional variational 4D data assimilation in ROMs. We are experimenting with better ways to look at the model data misfit. Some of our observations are relatively low resolution. I mentioned microwave sea surface temperature and salinity. So we're averaging the model appropriately to match it to those observations better. Same thing for HF radar currents, filtering out the tides, and altimetry. We're improving the way, from those of you that have some familiarity with the Maricou-Stopio forecast system, we're improving the way we specify our estimates of the error in the forecast by adapting that to the local Rossby radius, the natural scale of variability that gets much shorter when you go into shallow water and when you go to higher latitudes. And we are acknowledging that that is not isotropic. It's not the same in all directions. It tends to line up with features in the bottom topography. I won't say anything about the JEDI data assimilation capabilities. That's sort of working hand in hand with this project. Community. We are open sourcing the model configuration and the tools that we're developing to work with model output. That will be distributed to the community through an open GitHub instance. We're working with people at Tetra Tech to have an instance of this in the IUS Cloud Sandbox, so that ocean modelers at the different regional associations who want to experiment, perhaps running some of this in the cloud or using outputs, can do that through the IUS Cloud Sandbox. And that will make it easier for other groups to experiment with new observation platforms, or perhaps changes to the data assimilation methodology, things that are beyond the scope of all the things that we would like to try, but we want to make it easy for other people to experiment with that. And as I said, we will be producing tools for downscaling the whole regional ECCOFS domain to perhaps your local region of interest. I'm sure our colleagues at Caracous and GCUS are interested in doing that. If perhaps you want to run a biogeochemical model or an ecosystem model in conjunction with the outputs, we'll work to provide tools to help that work its way through. And if other stakeholder communities, some of you on the call, I hope, are interested in adding value, perhaps harmful algal bloom forecast or something, we will work with you to make those tools and the data you need accessible. Other sort of transition activities as we look at the 3-year time frame to move to operations. I mentioned that we want to prioritize opportunities for follow-on products, and this is part of the reason we're having this community webinar now. And we also are going to ask for some feedback. You're going to have some more polls from Emma, making sure we're on the right path, and is what we're doing fit for your purposes. We will be delivering boundary conditions to much higher resolution models of estuaries through our partners in National Ocean Surface. And we've also got other parallel projects where we're coupling the ECCOFS domain to the WRF and FV3 atmospheric forecast models and to WaveWatch, so that we have waves effects on currents, or perhaps people want to look at the effects of waves and Stokes drift moving sargassum weed or larval populations or whatever. And by producing data assimilative, high resolution analyses of the ocean state, we will be generating very good initial conditions for short-term coupled atmosphere-ocean forecasting, for example, to look at the impact of hurricane landfall. So that's our development path. That's all that I have to say, and I'll hand it back to you, Emma.
Thank you so much, John. That was wonderful. I really enjoyed the graphics that you added in. And so I am going to put another poll in the chat real fast with a little bit of initial multiple choice feedback that people can fill out to share their responses to that. But yes, the 3D glasses I especially liked. I didn't know you did cartoons as well.
So I've got my glasses out as a prop.
Yes. So thank you to everyone who's filling out this initial feedback poll. Alrighty. Answers coming in. Also, Roying, before you kick it off, Sherry's going to introduce you, and I also wanted to note that we'll have time for Q&A after this demo, so feel free. I see someone I think is already dropping questions in the chat, but feel free to put some questions in the chat and we will get to those very, very shortly. All right, the flow of the responses has slowed, and there will be also opportunities to provide more feedback later. So I am going to share the poll results with everyone, and can see people are especially interested in maps, which is good, and currents, which we'll get to this, but I really like how the currents are visualized, and we have some information about which types of data are most important. All right. Thank you so much, everyone. I'll pass it off to Sherry.
Thank you, Emma. Hi, everyone. It's my pleasure to introduce Roy-Ying He, who is a professor in the Department of Marine, Earth, and Atmospheric Sciences at North Carolina State University. He's also the founder and president of Fathom Science and a co-lead investigator on the ECCOFS project. Dr. He's research expertise spans from coastal ocean observations to development of prediction models, and today he'll be demonstrating the ECCOFS model in the current test harness with a sample of data. So thank you for being here, Roy-Ying. I'll take it over to you.
Well, thanks so much, Sherry. And thanks, John, for the nice presentation. I also like the cartoon and also the photos of the graphs. So let me share my screen. So let's see. Can you see my screen now?
It's still loading for me.
Still loading. Okay. Try it. Okay. How about now?
Looks great.
Okay, great. Well, thanks so much. So as part of this project, we've been as part of this project, we've been building a web interface, and part of the idea here is we are trying to push the next generation ocean forecast, and also serving the weather forecast system on the cloud computing, right? So in that case, we start using AWS web service to run day-by-day nowcast forecast, but also run a day-by-day web service on AWS as well. So we're using this web technology to build the foundations, so we can better serve larger communities in the future. If people want to have a map service or have a dashboard or even download the data, everything can be carried out by the cloud computing AWS. So this is a part of the effort trying to start building the elements. So as John mentioned, the ECCOFS model is using 40-bar data simulation, but the 40-bar data simulation has the two components. One is a forward model, and then the second part is the adjoint inverse model to bring the data simulation into the system. So as part of this web implementations, we took a two-step approach. The first step is to make sure we are able to run the forward model. So even before you bring the data simulation into the process, we want to make sure the system is able to be handled by web cloud computing. So what you are seeing here on this website is runs nowcast forecast without data simulation. So this is a part of our testing to make sure this operational system is able to running on day-by-day basis. Our team is moving towards bringing the data simulated 40-bar system into the same web platform. Right. So at this point, we're in the transition between forward model and also data simulated nowcast forecast. But as part of this user engagement meeting, we want to present this web interface to the team, to the community, and also get a feedback to see what type of visualization, the maps, the dashboard is useful. So we are here to take notes, and that will also be incorporated into the next version. So consider this as a version 1.0. So this is a beginning of us building this ECCOFS web interface, but we love to incorporate your advice and feedback so we can have a more functional and more user-friendly interface. So that's the background, but what you are seeing here is a ECCOFS predicted system. In this case, the color shading represents sea surface temperature. And for this first phase, we are running, again, day by day, 3 days prediction. So we are seeing yesterday, today, and also tomorrow, right? So we're looking at 3 days evolutions of temperature all the way to tomorrow, August 5th. Yeah, so we're looking at the ocean temperature, and certainly you can zoom in, zoom out. As John mentioned, there's a lot more very complex ocean features, frontal eddies, and also instabilities, both inside the Gulf of Mexico on the east coast of the US, and all the way to Gulf of St. Lawrence, to the Grand Bank, right? So we are looking at this entire region has lots of societal implications, societal applications, and also scientific processes that we are hoping that the system, the modeling system, can be valuable to contribute to. So this is the temperature. So one of the useful things is, in addition to zoom in, zoom out, you can also start sampling a time series, right? So you imagine you as a coastal user, I want to see a certain location in the Gulf, in the Caribbean, or on the East Coast Gulf Stream region, Gulf of Maine region, right? So this gives you this capability to sample the time series. So that's on the temperature side. You can also click on this button here to expand to see other variables. So we are seeing temperature, but you can also visualize other parameters like ocean currents. And you can also use there's a layer setting, so you can change the range of the value, right? So if I can change to 3 right? Then you can change to say 2. So you can highlight certain temperature range as you like. And then by doing so, the system will be automatically, hopefully automatically. Oh, I see. Okay, so 2. Yeah, so that will automatically zoom in the different features, allow you to highlight different processes using different color scale. If you so similarly, we can do similar processes or analysis using for salinity, right? So you can change a different color scale, different color limits to highlight certain region, and then you can also start looking to ocean currents, right? In this case, you can sample the time series of different location of the surface currents, and also you can zoom in to different regions to start looking to the circulation, the transport, the connectivities. One of the features you can also do is to go down here, so you can add a different number of particles, and also adding different changing different width of the lines, right? So this will help you to visualize circulation, the smaller scale processes, and transport, so on and so forth. Right. So this is again some initial functionalities we're building in. So far, the system is supporting surface fields, but we are building capability to support the visualization, user defined dashboard for the entire 3-dimensional ocean states. And certainly, as we are moving to the next phase, which is adding data simulation, we're also building processes about the users to see the type of observations that we are ingesting into the DA system. So imagine if you zoom in certain location, and then we should also highlight the locations of observations and also different observations. So the design goal here is, again, trying to make this a useful tool and useful dashboard for the community. And we also start, excuse me, we're also talking about how we can make the data available, right? So in addition to the map and also this interactive user interface, ultimately, many of our users are interested in the digital output. So we can think about how we can build a either thread server or S3 bucket, allow user to download the data, to subsetting the data, so they can run their sub-regional high-resolution models. And this is all in the development pipeline, but we'd love to hear your inputs and also let us know what is the most useful features and also functionalities that you're looking for. And then we'll be building this type of functionalities and features in the coming months and years. So the link to this website is very simple. It's called ECCOFS.patentscience.com. And I will be posting this link in the chat window in a minute. But feel free to come to this website to play yourself. And we are, again, as I mentioned, routinely update 3-day predictions about we'll be updating every 9:30 a.m. in the morning. And then in about next couple of months, we will be transitioning into a data simulation nowcast forecast. So stay tuned and let us know how we can improve this dashboard interface and also how we can best share the data, the information to the community at large. So thanks again for your interest, and we'll be happy to answer any questions you might have. Circle back to Sherry and Emma.
Yep, thank you so much, Roy. That was awesome. Great demo. If anyone does have questions in the audience, please feel free to raise your hand, but there are some in the chat, so I can go ahead and start reading those off. This one was after John's presentation. Could you please provide more information about the biogeochemical opportunities that could arise from your system? And are there any currently ongoing activities in that area?
Yeah, thanks for that question, Jose. We, as a part of the ECCOFS development itself, we are not envisioning working on coupled biogeochemical models ourselves, but this is a ROMS, Regional Ocean Modeling System model. There are several ecosystem models that ship with ROMS right out of the box when you download it from GitHub. There are several others, dozens actually, in the community of people doing a different work that's based on the hydrodynamic core being ROMs. So what we're saying is we will make outputs available so that if you want to rerun our data assimilative analysis, but add a biogeochemical model to it, then those of you that know how to do that are welcome to do so, and we would encourage and love for people to do that. In the context of the Maricus operating forecast system that operates right now, the Doppio domain that I showed in my first couple of slides, we do have a joint project with Margie Friedrichs and Pierre Saint-Laurent at VIMS, Virginia Institute of Marine Science, where we are doing exactly that. We are running an ecosystem model that Pierre and Margie have used for their estuarine and coastal biogeochemical model, a variant of Katja-Fennell's model that we used some years ago to look at nitrogen cycling and carbon cycling on the Mid-Atlantic Bight Shelf. And we are setting things up to run that operationally so that every day when we produce a ocean physics data assimilative estimate, we'll be producing a companion biogeochemical model, sort of a prototype forecast for that. So that work is underway, but we certainly invite inputs from anybody on the call and in the community who would like to have a sort of a leg up on how to utilize the ECCOFS outputs to support their own regional BGC modeling work.
Great. So the next question is for the 5-day forecast, the first 48 is HRR and the remainder is GFS. Is that correct?
That is correct, Travis. Yes. Yeah, so, what's the impact of that? The HER model and that transition. Well, if we had the high resolution rapid refresh covering the whole domain and a 7-day forecast, we could do that experiment. But at the moment, we just don't know. But the models are very, very consistent. When you just look at the HER forecast, the GFS forecast within the HER domain, there's not a lot of difference at the kind of scale that's forcing the ocean. And it may be that the differences are less over the ocean than they are over land, but we're looking over the ocean. So yeah, I don't know the answer to the second part of your question.
Okay. From Dave Jones, there are a few questions in the chat, and the first one is, how close to the coastline does the forecast reach?
So it goes all the way to the coast, and our version of the coast is how well that renders itself in a 3-kilometer grid. So it's not perfect, but it's so that's as good as we can do with the resolution of the model that we have. I mentioned that we've talked about putting the framework there. If someone wants to run a nested model inside ECCOFS, we already have code that would generate a ROMS domain and boundary conditions from ECCOFS output. So if you wanted to create a much higher resolution model and then force it at the boundaries with ECCOFS analysis, that's a straightforward thing to do. We've done a little bit of that ourselves in a project for US Coast Guard, looking at the impacts of wind farms on surface currents, where we downscale by a factor of 5. So we end up with a model that's at the kilometer scale or less, and that actually works very smoothly. We've got procedures to do that. I think you also asked about how the ECCOFS solution at the coast would inform local inundation studies. So what we are capturing is the low frequency variability in the sea level that's associated with the large scale ocean circulation. So think in terms of mesoscale features like meanders in the Gulf Stream that might push up against the South Atlantic Bight coast, or Gulf Stream rings that would impinge upon the continental shelf or into the Gulf of Maine, and maybe driving low frequency sea level variability. In work we've done with the Doppio analysis system, we know that we are much skillful at getting low frequency sea level variations from the seasonal scale out to 10, 3, even 2-day timescale variability. And we attribute that to the fact that we're assimilating direct observations of sea level height from the altimeter satellite constellation. And we have gone to efforts to, there is a large coastal altimetry community that has worked over the last decade to enable people to reliably use satellite altimeters very close to the coast. You know, a lot of people will tell you, oh, you can't use it on the continental shelf. Well, that's simply wrong. There are steps you can take to appropriately process satellite altimeter data that'll let you use it right up to maybe 4 to 10 kilometers from the coast. And we have been doing that. And I think that is what's contributing to the added skill we're getting in low frequency sea level variability. So then if you have an estuary model like Chesapeake Bay, so you're looking at, you know, sunny day flooding in Norfolk that's associated with low sea level due to low air pressure or other features in the ocean, in the deep water, we will be providing the boundary conditions that would help an estuary model, for example, capture that low frequency variability, and then having a high resolution adaptive mesh grid within that estuary would be adding skill at the short length scales and the high frequencies in time.
Great. And I think his third question was, what does transition activities mean? Is this a focus for end of project or something that you want to get involved in now?
Part of the reason to have this webinar is we want to open that conversation with our stakeholders, make sure that we're on the right track, producing the sorts of products that you care about, and get some feedback on, you know, what's the most important thing to forecast for you? Is it low frequency sea level? Is it, you know, velocity on the continental shelf? Is it the bottom temperature because you're fishing out there, you know, you're trawling or something? We want to know what you need to know from an ocean forecast system. So we don't want to get to the end of 3 years and say, okay, here you are, Weather Service, here's ECCOFS, we're done, and then have people say to us, well, that's not really what we wanted. So we're definitely here to open that conversation and would like to hear more from people like you, Dave.
Thank you, John. Edward also had a question in the comment about revisiting your first slide. There was a graph inset in that slide that he had a question about. Edward, I don't know if you want to unmute and ask those questions. Feel free.
Yeah, that'd be great if that first slide could be brought up again.
Clicked on the wrong thing. Do you mean this?
You had a slide that had a bar graph insert. Yeah, that here. So you talk about the Coast Guard asking, I think, 1,100 times a month for data to support their SAR ops, their search and rescue ops. But in the bar graph, it seems to me that the data from the HF radar system, NOAA's HF radar system, is collected separately from the ROMS data, or does the ROMS data include the HF radar data? I'm trying to get a sense of exactly what data is being provided, or the source of the data being provided to the Coast Guard.
It's a astute question. So the environmental data server presents a SAROPS operator with a wealth of information. And so this includes measurements of ocean surface currents from the HF radar network. So an operator can look at, you know, what does the radar show us for the currents, you know, 5 hours ago, 12 hours ago when somebody fell overboard. In our ocean forecast system, Doppio, one of the data sets that we assimilate to improve our ocean state estimate, my X star, are those HF radar currents. So it's a bit of both. So of course, our ocean surface currents in the Doppio model aren't going to exactly match the HF radar because we're putting there's other information going into this. We've got a dynamic model with the winds, and we're also reconciling other information about ocean surface currents, which includes those altimeter satellites that give us sea surface slope that affects mesoscale variability. So our forecast is informed by those data. It's not exactly those HF radar data. And of course, from the SAROPS point of view, you can't get a forecast from HF radar. That's an observation of something that happened yesterday or in the last few hours. And we're taking that information and saying, this helps us get a better idea of what the ocean state looked like right now. And then we're making that leap of faith of if we've got a better estimate of what the ocean looks like now, that will help us provide a better forecast. But the only forecast products available in SAROPS are obviously model based. And they have multiple models there in the environmental data server. And these operators, there's a little bit of expert knowledge in there. Do we trust? Maybe we don't trust the Doppio model in Long Island Sound. Maybe we've got something better. They're free to make those judgments themselves. We're presented with the data that's in front of them through this EDS product.
Thank you. That's very helpful. Appreciate it.
Yeah, thanks for the question.
All right, I think we have a couple more minutes to wrap up some more questions. Ellen asked in the chat, do you know how the model handles extreme events like extreme precipitation and river flows, hurricane conditions, etc.?
Thanks, Alan. We've certainly run the model through, multiple years, and it runs stably and handles those things. We had to do a little bit of work on, yes, with extreme river discharge can be a little bit problematic. It can generate some bad artifacts in ROMs. Sometimes the salinity goes negative. Nobody ever wants that, but we're working on improving that performance. A couple of things with respect to extreme weather is some of the experimentation we've done with an earlier prototype of this model, which we called WATL, the West Atlantic model. We did some simulations of Hurricane Isaias coupled to an atmospheric model, and we did show that when we assimilate ocean observations into the ocean state estimate, we get a greater skill in the short-term forecast of the hurricane, mostly in the ocean response to the hurricane, which we put down to having a better estimate of the ocean heat content, because we've got observations informing that. And one of our sort of development test projects and associated with ECCOFS is we're revisiting Hurricane Dorian at the moment. So we've taken a subset of the ECCOFS domain, as I was saying, and we are running that coupled to an atmospheric model. And we're setting that up also as a development platform to couple ROMs to WaveWatch 3. So coupled modeling with WaveWatch 3 or with the FV3 atmospheric model or WRF is not a part of ECCOFS, but everything we are doing in our ECCOFS development is making that modeling system functional and available to someone that wants to do that sort of coupled work. And so, adding in waves, if you're interested in extreme weather, is the impact of waves on the coast during a landfalling hurricane. We are certainly doing work that's complementary to that. And we have updated the bulk formula that calculates stress and wind stress and air sea fluxes to use the core 3.5 algorithm from Jim Edson at Woods Hole. And that's been adapted to perform better at very high wind speeds, better than the previous 3.0 version that was in ROMs, if you're a ROMs Insider modeler. Does that help, Helen? I hope.
All right, I think that is about all the time we have for questions right now, though I do expect to have a few minutes at the end for some more, so feel free to please continue to put your questions in the chat. I'm going to pass this back over to Emma.
We're going to have one more quick feedback poll, just 2 questions, and then we'll have plenty of time. We'll have another 15 minutes at the end for more full group Q&A. But next, we are going to transition into some breakout groups. We'll turn off the recording, and you'll have wonderful moderators and note takers who are going to take anonymized group notes in each group.